Okay, we're given a system of equations, and we're asked to find a solution of the system using Gaussian eliminations. And we're going to use note number 126 to do this. Step 1 in note 126 tells us to write an augmented matrix from the system. And everything's lined up perfectly, so it would be very easy to translate into our augmented matrix. There's a 2 in the x column, and then there's a -3, and then there's a -1 constant on the right side. And the next, and that's row 1, by the way. And row 2 has a coefficient of 3 in the x column, a -2 in the y column, some space, and a +1. And that's row 2. And if you want to, you can put the dotted line indicating that there is an equal sign there. You don't have to, but you can. Okay, that's step 1. We just translated our system of equations into an augmented matrix. Step 2, we're going to use row operations to get this equation into lower triangle form. Lower triangular form. Okay, and I'm going to be very careful and show you how I'm doing this. First of all, we are going to do row 2 minus row 1, and that will become our new row 1. That's the plan here for the first step. Now, without showing you the actual work that I did to get the following result, I showed you in the previous video how you do this and how you take the result and, in this case, replace row 1 with what you get. So I'm going to do the work in my head and just write the resulting new matrix that I get when I replace row 1 with the result of row 2 minus row 1. But I will leave row 2 alone when I write this result. So this is just the result. And if you want to do the details, you can work it out yourself on the side. So the result will be, in the first row, the coefficient 1, 1, and then 2. That's row 1. That's the new row 1 because I did that row operation to get it. But the next row, row 2, remains unchanged. 3, -2, +1. That's my row 2. Okay, so you see what I did? I was concentrating on this number 2. I needed to get it to be a 1 to get the lower triangular form. So I did row 2 minus row 1, and I replaced row 1 with that. Now I am going to work on getting this dude here, 3. I want him to be a 0. And to do that, I'm going to do the following. -3 times row 1 added to row 2, and that will become my new row 2. Now, whatever it takes to get that is what I'm doing. I'm thinking about this, and then I come up with this plan. Now I'm showing you the result of actually doing the row operation, -3 times row 1 plus row 2. The result will replace row 2, but row 1 will not be replaced in this step, so I leave the 1, 1, 2 for the row 1. And for row 2, I write the result that I just got, and that's going to be a 0 in this column, and then a -5, and then a -5. That's my row 2. And you'll see how I succeeded in getting the 0 in the first column on the bottom. Now, I would move to the next column, which is the y column. At the top, there's a 1, so I don't need to do anything to that. But down below the 1 is a -5, and I want that to be a 1. All right, to get lower triangular form. So in order to get that 1, I am going to do the following operation, row operation. I'm going to go -1/5 times row 2 will now become my new row 2. You know, and we don't all do this the same way. We might get at it at along a different path, but at the end, we will be at the same conclusion. The first row 1, is going to be unchanged. It's 1, 1, 2. That's my row 1. But row 2 will be replaced by -1/5 times row 2. So I'm going to have a 0 and a +1 and a +1. That's my row 2, my new row 2. Okay, so do we have lower triangular form? Yes, we do, because you see on the diagonal, we have the 1s. And below the diagonal, the lower triangle, we have a 0. Now, if it were bigger, we'd have more 0s down there. But as long as we get the 1s on the diagonal and the 0s down below that on the left side in the triangular form, then we know we're in lower triangular form, and we can go back to our note number 126 and see the next step is to translate back to a system of equations. Step 3, back to system. I urge you to go back and read note number 126 for these steps. Back to system. Okay, now remember, the first column are x's, the second column are y's, and then even though I didn't draw it, the dotted line indicates that there's an equal sign, and then the constants. So that would give me the following system: x plus y equals 2. And then down below, we have 0 times x, so don't write anything. Then there's y equals 1. And I'll put my curly brackets for the system of equations. And now I'm just ready to do the substituting, which is step 4. Step 4 is back substitute to solve for all the variables. I'll just write back substitute. And this is all coming, these steps are coming from note number 126. Okay, so we're going to plug that into the top, the first equation, and we'll get x plus 1 equals 2. We'll solve for x. X is equal to 2 minus 1, which is 1. Okay, we're almost there. Now let's go to plugging that into, well, we don't have to plug it in anything because we see here that the y is equal to 1. Now that we found that the x is equal to 1, that means the solution of the system is the ordered pair xy equals 1 for the x, comma, and 1 for the y. Okay, so we got one solution, and so these two equations that we started with were independent of one another. If they weren't independent, we would have more than one solution. We would have infinitely many, right? Independent. Just a little comment about this type of system, and we're done with our solution.